invite Dr. Davood Roshan today for the first as the first speaker. He's a lecturer about the bar at the Statistical Science in Statistical Science at the School of Mathematical and Statistical Sciences, University of Galway. He's also a funded investigator at CÚRAM, Research Centre for Medical Devices. Davood's research perfectly aligns with national strategic plans and sustainable development goals to develop innovative data-driven approaches. His primary research focuses on developing advanced statistical methods to identify meaningful changes in the longitudinal monitoring of clinical outcomes, enabling more effective patient monitoring and early diagnosis. His interdisciplinary work spans healthcare, medical devices, and sports science, with methodologies widely adopted in both academia and industry.
Thank you. That was pretty much my talk. Thank you. Okay, hi everyone, and thanks for the nice introduction and for having me today. My name is Davood Roshan, and as introduced, I'm a lecturer in stats in the School of Mathematical and Statistical Sciences and a funded investigator at CÚRAM. So today I decided to talk about challenge your limits. So I know the title might sound a bit vague, but hopefully by the end of this presentation, you all get a sense of what I mean by that. And then if you have data or research problem that fits the topic I'm going to discuss, maybe we can have some discussion around that too. Okay. So, so by just raising your hand, have you ever given any blood tests at your lab? Oh, okay. Or urine test? So I'm sure most of us have done at least one blood test in our lab. And hopefully if you do, you get a message like this, which I got a few weeks ago, that please be advised that we have received your blood results and they are all normal or within acceptable limits. So we understand the normal aspect of it. So it seems everything is okay. But then they say, okay, it's within the acceptable limit. So the question is, what is this acceptable limit? And how we can make decision based on that. So usually when you do this sort of blood test, so there are a lot of parameters will be measured as part of your blood test. What the laboratory people do, they will compare your blood test with some ranges. Like you can see that they often have a small and large value. And if the value test result falls in that range, so it seems to be normal. If it falls outside that range, so it seems to be abnormal, like the case you see here, right? But here is, for example, a sample report of such blood test result. Like, for example, in the first column, you can see test different parameters that has been measured, their values, their units, and finally this last column, which is the reference range associated with that. So usually, so even yourself, you can look at those values and convert your test results to the normal ranges to see if your value is normal or abnormal. Like here, you can see that the cholesterol level and the LDL, they were both outside of the outside of these reference ranges, so which suggests that they might be abnormal, right? So this is a very useful, I don't want to say diagnosis tool, but this is very useful in identifying if there might be any abnormality or not, because if the values are up, then probably doctors will advise you, or they may just do some intervention, or they may need to do some follow-up checkups. So, but they are very useful when we have only one measurement or one test results. Like, for example, if you look at this graph here, so the area I shaded in blue is showing the reference range for PSA, which is a biomarker in diagnosing prostate cancer. So you may have already know that. But the range for that is for certain age group is between 0 to 6.5. And let's say we have a subject whose test result is around 2 here. So that perfectly falls inside the range. So you may think, okay, that's normal, well done. Okay, nothing else. But let's say this subject gonna continue and do a routine follow-up, because it's important to check your PSA like every 6 months, every year, just to make sure that you are within the limit. And then you can see the trajectory for this subject. And if you look at each of these values here, so individually, so they all falls within the acceptable limit or the threshold. So they seems to be all normal to me. And even the doctors, if let's say they ignore all this, they may look at this and say, okay, it's out inside the reference ranges. So that's fine. But the problem is these sort of reference ranges that is defined in practice, they will be very useful when we have only one test result. But when you have a series of measurements, so not only you need to take into account the variability that exists from one subject to another subject to another subject, but also you need to take into account the changes that happens within the same subject over time in order to say whether that change or that value was significantly outside the norm or not, right? So that's why to overcome this in practice, so I have developed or proposed the concept of adaptive reference ranges. So adaptive reference range essentially are the same sort of reference ranges, but each time we have a new measurement, we try to learn from the previous data from that subject and data from the population of healthy individuals. We'll combine these two information and we create a new reference range. So it's not only personalized, it changes from one subject to another subject to another subject, but also it's adaptive. So it changes from time to time, depending on your previous records or previous data. Right, you can see, for example, here, that's the adaptive reference range for the same subject. And you can see that the last value here, now it's outside of the reference range or personalized reference range. That was something you could see here. So there was a bit huge jump here, so which could be a bit concerning, but the actual reference range couldn't detect that, right? So here is another example that shows the idea a little bit better. So this is the case that we have. This pink area shows the reference range, just the population norm for one particular outcome. And the red lines are, those are red, but here it's shown in black. But those trajectories for a particular individual. And you can see that there are a lot of values here that falls outside of the range, which you may wonder that maybe they are abnormal. But in fact, they are not, because if you look at the personalized reference ranges or adaptive reference ranges, they all falls within the individual trajectory. And it's interesting to see that the last one, which was kind of normal compared to the population, now it's abnormal compared to the previous measurements of the same subject over time, right? So that's actually the concept of the adaptive reference ranges. So now let's talk about the maths or methodology behind it. So don't worry, I don't want to bother you with that. So it's just I'm going to show you that there are advanced statistical methods behind that. So essentially what we are trying to do is we are trying to combine the variability that we have from subject to subject in a population. That variability is what in practice has been used to define those basic reference ranges. We try to combine those with the variability within the same subject to kind of make it more personalized and adaptive. So, but if you're interested, you're more than welcome to look at our two papers, one published a few years back, which kind of introduced the concept of adaptive reference ranges with multiple methods. And this one, as you can see, the title is Adaptive Reference Ranges from A to Z. It's just giving you a full guideline of what methods you need to use. And so it's essentially from A to Z to learn everything about the adaptive reference ranges, right? Does it make sense? Okay, so now what I'm going to do is I'm going to show you some applications. So I don't want to make this presentation very theoretical. So let's see what are the other applications, because you may wonder that that's only applicable in medical diagnosis or laboratory test result. The answer is no. In fact, every time you have any sequential data that has been measured within the same subjects or a system or an environment, and you might be interested in defining any anomalies or atypical values, you can think of using this sort of reference ranges or adaptive reference ranges. So one application that we applied this was in glucose monitoring. Like you know that these sensor devices for patients with type 1 diabetes, they use these devices to continuously record their glucose level. What happens is they often will be compared with against some static reference ranges. But what we are going to do is we have made it more personalized. So we are learning from the variability within the same subject, especially for glucose monitoring is quite vary from subject to another subject. And again, within days, like for example, morning, in the afternoon. So there are a lot of adjustment you have to make. And you can see that in this case, the adaptive one is wider because this subject had more variability in their glucose level. So that's why you can see that some of the values which are abnormal compared to a static one, they may be normal compared to the personalized method. So the other application we implemented our method was in a sports science. So, like in your basketball exercise. So if you monitor your activity, like CRP, I don't know. You probably know what CRP is. CRP is one of the biomarker C-reactive protein level that kind of gives you an indication of the inflammations in your body. So, and this is quite common biomarker that will be measured on professional football players in Premier League. And what they do is they measure the CRP before training and post-training, and then they will monitor them over time. And if they falls outside of certain values, they may indicate some injury or may indicate some fatigue in those players. So we applied, but again, like any other biomarkers or any other practice, they will use fixed reference ranges for that. But then we have proposed the concept of adaptive reference ranges in that domain, and we show that how nicely it works as an early warning system. So something that we indicated is it's not a diagnosis tool. We don't say that if it falls outside the range, personalized range. So definitely something going on. So, but it is an early warning system. If your value falls outside of your personalized reference ranges, it means that something is going wrong here. So you need to go and investigate that, maybe do another check, another test, or maybe talk to doctors or PCO or any other person, right? So that paper is also there if you are interested in. So the other application is environmental monitoring. So like you can see that how important these days is to monitor like environmental index and pollutant level in the world globally, and also in Ireland. There are a lot of folks in that area. So for example, I was interested in the PM2.5, which is one of the pollutant index in Ireland. So it's the WHO threshold, the daily threshold for that is between 0 to 15. So anything under that is totally fine. But I was just looking at one of the stations in Ireland, and you can see that this is the variability over time for that part, over days in 2023. And you can see that there are certain spikes that they are also still inside the WHO reference ranges, or actually threshold, but they fall within outside of that station kind of normality, or actually the pattern there. So therefore, that might indicate something going on here, maybe needs further investigation. So this is just a demo. I didn't implement my research yet on this data because there are a lot of things that we need to consider here. Okay, so that's, okay, one more example here. So that's about your activity monitoring. If you have smartwatches and if you're interested to see how you are doing day to day, like how many steps you have taken for the past few days, whether you do normal, compare yourself or not, so you can implement this as well. So now the question here is, so all these methods I discussed, the main problem was we only had one outcome of interest, and we tried to look at the trajectory or the variability in that outcome. But the question that may come here is, okay, what about the other factors that may influence that, like the age, gender in clinical biomarkers, or like seasonality effect in like the PM2.5 monitoring or any other domain? So the answer is yes, that's a good question. And that's one of the work that my PhD student was doing over the past year. So I'm going to show you this with one example, that how we incorporate such covariate or such a factor into the model. Like, again, this is a reference range, personalized adaptive reference range for a particular outcome. And you can see that the first three values are outside of even the personalized adaptive reference ranges. So that's a univariate one. That's just the one that I was discussing. But then we try to extend the model to incorporate the gender as a factor into the model. And now you can see that the adaptive reference ranges has been shifted up a little bit at the beginning, but then it mirrors more or less the same as the univariate method. And that's a very interesting result, because that's very important at the beginning. You learn data, because this is a personalized adaptive reference ranges. So it becomes more personalized as you have more data. So it means that at the beginning, you heavily rely on the population data, but then after a certain time, you become more personalized. And that's what exactly you see here. At the beginning, we are learning from gender-specific characteristics in that population, so that's been shifted up. But then after certain values, then we rely more on the individual measurements, and now that's why the two methods gives you more or less the same result. So the other thing is, so of course in practice, so you can see that sensor devices has become very popular these days. So like you can have sensor devices, medical devices that they measure multiple outcomes at the same time for the same subject over time. Like those glucose one I gave you, like look at the blood pressure sensor devices, like those continuous monitoring blood pressure devices that they measure your systolic and diastolic at the same time over time, or a lot of other vital factors. So then the question of interest might be, okay, how do we, so instead of being interested in one particular outcome, how we need to think about whether the collection of these values, like systolic, diastolic together, their changes over time, is it significantly abnormal or not? So instead of looking at each of them individually, we're going to combine that. So that's what we call multivariate adaptive reference region. So instead of having a range, which is in a 2-dimension, now we have a region which you could think of as a ellipse or as any other geometric shape that changes over time. So we are working on that, but just as a demo to show you, like, let's say we have two biomarkers, two outcome of interest that changes over time together. So you can think of the reference ranges will change to reference region of these forms here, these two shapes. And this is the animated version of that the changes shows different time frames. And the square here kind of shows the region at that particular time values. And if the combination of those two biomarkers falls inside the range, then that's normal. If it falls outside the region, then that may indicate some abnormality, which consider the correlation or the dependency that exists between those two outcomes, right? So just to wrap up, so that was the whole idea. So if you are interested in implementing, if you believe you have data that may fit to the same questions of interest, so if you're interested in defining anomalies, so there are two web-based apps already online there that you can just go to those links, upload your data, and generate these personalized reference ranges for different contexts you have. So the one on the left is mainly for the univariate one, which you don't have any covariate. The one on the right is mainly for covariate adjusted one, right? So that's actually our take-home message. So, so when I say challenge your limit, so I mean, every time you see these reference ranges, think about them more carefully. So think about that, whether there is a component of within subject or within time variability for those limits or not. So if so, why not using adaptive reference ranges? But we are happy to discuss this more in detail if you have any data or if you have research problem that somehow mirrors this topic. So I have my email address here, but you can find me on my page. And here is my research team that each of these people are working in different aspects of the concept. Like I have 3 PhD students and 2 postdocs. Aspen is sitting here, who started just last week. So we are happy to help you. Okay, thank you. Any question? Yeah.
Very interesting talk. Thank you. I was wondering what would be the, let's say, minimum number of data points you'd have to have before you can say with about 90% confidence that this is a good adaptive reference range?
That's a very nice question. Thank you. So our result has shown that, so of course, the more data point you have, the more accurate it would be. Like, for example, there is no point of having adaptive reference ranges for 2 or 3 repeated measures. So I would say minimum, every time I'm going to work with any data, so I will usually concentrate or focus on subjects who have a minimum of 5 measurements. Like I say 5 to 7 or 10 is ideal, but anything more than that, that's perfect. Thank you. Yeah.
Thank you. Very nice. I'm wondering, is it reliable to use these applications in clinics or hospitals? Because, you know, in clinics and hospitals, we have a lot of data from years and years, you know, from the patients. So, and it's very difficult to go and, you know, compare from years ago for one single patient, you know. So is it really that much reliable, this kind of applications?
Okay, so that's also a very good question. Well, first of all, so that's the whole concept. So if you're gonna apply it in any domain, like for example, in glucose monitoring, you need to make the model more specified to work in that domain. Like for example, you need to consider the within day changes of variability or temporal changes that exist within day for those patients with diabetic or blood pressure issues or hypertension. So I would say it gives you an overall sense of the trajectory and how that subject, but if you're gonna use it in real practice, so you have to do clinical trials, and you know, it's not like just you say, okay, the method is there. So we can show and provide evidence that that works for most of the cases, like the example I've given you, that was pretty much confirming that. But if you're gonna use it in HSC, in doctors, GP, or a practice, then I would be extra careful, because it doesn't work there, but you need to provide evidence, clinical trial that kind of confirm the results there, because that would be very sensitive. But I would say, I always say that this is not a diagnosis tool, it's a early warning system. So it kind of gives you a sense that you need to do further investigation, or there's something going wrong here, or something is abnormal. So think about it. So if it's just a measurement, do another blood test in 2 days, see if the value is still up or not. If that's the case, then you need to be worried. If not, then probably that was just a coincidence. Another question?
Oh, sorry.
Yeah.
I was curious, like, so you show like first the personalized limits, and then you say you can correct by gender, for example. But why is in the personalized limit the gender is not already kind of taken into account?
The model at the moment, so what it does, so let's say you have a bunch of data, you have the sum of interest and the gender, right? So what the model does, the initial version of the model does, so it look at just the outcome and the variability with the outcome. There might be some changes from between males and females in those outcomes, but the model doesn't understand that unless if you specify that gender is in the model. So it's like any other statistical model that if you fit a regression model, so you might be only interested in the variability in Y itself, or you may be interested in variability in Y, changes in Y, adjusted for the effect of gender. So we are trying to make those adjustments. Like that's why it is not included at the beginning, because it doesn't learn. So it just thinks all the boys are from the same sort of people. So
But
I don't know if I answered.
I'm not sure. So, but the personalized one, is it like for one person?
Yeah.
Yeah. So let's say for me,
Okay.
I'm doing like measurements, and then we have this limit that is adapted to me.
Yeah.
Since I'm a
So
woman,
let me tell you, so there are different methods that works for adaptive reference ranges. One is solely on the individual measurement. So they ignore the population totally. So they say, okay, I have your measurements. I just look at your next measurements compared to your previous one. In that case, gender or any other cover doesn't make sense. But the model we are proposing is you not only need to look at those changes within the subject, but also you need to look at the other individuals in the population. So therefore, that's important to, if you don't look at the gender, you will compare that person with everybody. Yeah. If you look at the gender adjusted model, so then you will concentrate on people with the same characteristics.
Yeah, mine is just a query, really. Have you looked at the cardiovascular space with this, or have you engaged with?
Yeah, we are working with Drake and some other colleagues in the School of Medicine to see if we can implement that for blood pressure monitoring, and how that can be related to cardiovascular disease and then hypertension. So yeah, I don't know, what do you mean exactly by cardiovascular?
That's exactly what I mean. Yeah.
That was, we can talk later, but yeah, we had a funding call on that, so working on that. Yeah.
Super. Have you engaged with the ARC program?
ARC?
Yeah, the ARC hub.
Yeah. So yeah, we did. I tried that one last year before the proposal, the main proposal wasn't successful, but then hopefully try again.
Yeah, they'll have another call.
Yeah, I know. Yeah.
so
That would be, yeah,
This is a-
look at how that could be implemented in medical devices directly, like those glucose monitoring. So they are just based on just static reference ranges. So if we can implement our algorithm in those devices, then that would be kind of a more personalized diagnosis of early warning system for those devices. Yeah. We can have a chat about that. Yeah. Any other questions?
Well, if not, we can.
Thank you.
again.
Thank you for.